get started. Definition from TMS 402-602, which is the structural masonry code, says masonry veneer is non-structural. It is supported vertically by the foundation or another element and laterally through anchors to the backing. In TMS 402-602, anyone who's been on code committees knows how big definitions are. I'm going to be using the term masonry anchor all the way through this presentation, despite most of the industry referring to these as brick ties. So why does this matter? So show of hands, who in here has designed a brick masonry veneer? A few hands. A few more than I actually thought I would have. Second question, who in here has designed framing for a building later clad with brick masonry veneer? More hands. So why do we care? Load path. Lateral loads are applied to the surface of the masonry veneer, and we're relying upon our lateral load resisting system to resist those loads. And we also care because of life safety. Bricks are not necessarily lightweight. If they don't stay anchored to the wall, that would be quite a big headache. And then lastly, we want our buildings to last, which goes into durability, so I'll hand it over to Dave.
Thank you. So this first example is a failure of anchored stone masonry, a little different than brick masonry veneer that we're going to come back to in a few minutes. But it is such an interesting failure. I like the picture so much. I used it on the cover of my book, Failures. And it is, oh, we got to turn off one of my, yeah. Okay. So I used it on the cover of Failure Mechanisms in Building Construction. But what I especially like about it is the two guys standing in the background with their arms crossed going, I don't know what happened, it just fell off. Well, we do care about what happened, and that's the first practice area that we come to this subject from, is that failure investigations. We need to understand material behavior in order to investigate why failures occur. The second major practice area is that we're going to design a solution for these failures. So here the brick masonry has been entirely removed. You can see an abject failure of the structure behind it due to trapped water behind the masonry. And so for remedial design, we want to prevent a recurrence of the same mechanisms. And the third practice area that we're considering is for new construction consulting. We want to prevent these failures in the first place. And for all of these, the common thread is durability. So everyone understands duration, but the concept of durability is actually hard to grasp, and the reason is that it's hard to visualize. So we're going to give you some visual cues today that we hope will drive home what durability is all about, especially related to masonry. So we want things to last, and durability is also green, so it's very popular right now because it's the very essence of sustainability. We want to reduce waste and keep building materials out of the landfill longer. And so we select products with optimal design life. Now notice we don't say longest design life. And the reason is we can gold plate things and make them last for eternity. However, that's not economical. So we have to balance performance and economics in all of these judgments. And then assuming that we grasp this design life concept, and we're going to look at the building blocks that come under these, then the next one is service life. We want to achieve the longest possible service life for the products that are selected. Towards that end, we created the Durability Lab at the University of Texas at Austin. It's at the Pickle Research Center. It's a nonprofit institution. That means it has no outside influence. It's one way of giving back. So make no mistake, most of our income comes from failure investigations. This is other people's losses. It's a very lucrative practice, but it's all coming out of performance problems that have occurred, and these losses generate enough free cash flow for us to plow some back into research, publishing, and public speaking. We research, we test, we publish, we do public speaking, and visitors are always welcome to the lab. Also, you're all welcome to come visit and see these things in demonstrations. So some of the recent research and articles we've published are on water-resistant barriers, architectural metals, water repellents, tapes and flashings, stucco, exterior doors, bearing pads in parking garages, concrete masonry waterproofing, elastomeric wall coatings, sheathing, and infrared testing, especially in hot climates, and the limitations on that technology in places like Texas. Balcony waterproofing, high-performance sealant, and what Bobby's going to come back to in a minute, one of his deep areas of expertise is in masonry wall anchors, and we've done quite a bit of testing in that area. So, before we come back to the brick masonry, I want to give you some durability concepts. The first building block is design life. So, design life is a predictive estimate. ASTM E2018 describes it as the average expected useful life. I emphasize expected because that's the key to this concept, the first building block. So if we look at whole building design life first as the lowest building block, we have recognized structures that are institutional, courthouses, museums, libraries, where the expectation is that the design life is going to be over 100 years. And at the other end of the spectrum, we have code-defined temporary buildings where the permit is only for a short period of time. The building cannot typically last more than 5 years, or you're violating the original permit concept that it was a temporary structure. But what those bookends leave out then is the entire built portfolio, which is like the building we're in. What is the expected useful life of this building, of most residences, of most commercial office buildings? That's what we call the mushy middle. That is not well defined at all in publications or in industry. And so it has to be defined for the project, and it rarely is until there's a failure. So let's pretend that we all agree that this is a 60-year design life for the typical building. This is not really a consensus out there. It only gets discussed when there's a failure, and then nobody's ever thought about it before, but they thought it would have lasted longer than this. So, but in order to move on, we can't spend a lot of time on one concept. So we're going to move on and just pretend that we all agree that 60 years is the design life for the whole building. Then we look at the component design life, the decisions that go into the materials selected to support that. And they have to be compatible. So there are 3 basic categories for design life of components relative to the building's design life. Those are replaceable components, maintainable components, and permanent components. But we have failures. We have durability failures in all 3 categories. And I'm going to show you 3 examples from masonry buildings that have suffered this type of failure. So the first example is a failure of a replaceable component, which is simply the sealant joints in the exterior brick masonry veneer. So we diagram that, again, trying to create some visualization of these different concepts as 4 separate life cycles for the sealant, because it's a different sealant every 15 years or so. So there are 4 disconnected arrows summing up to a design life of 60 years, but the component design life is only about 15 years for each of these individual design life cycles. However, when the actual performance is less than 5 years and we're having to replace the sealant prematurely, then we still have litigation over even this replaceable component. And so we diagram this first concept as 4 disconnected arrows. The next one is an example of failure of the maintainable component. Here it is the brick masonry itself. So this veneer is expected to serve for the life of the building, but it is understood that it requires intervention, that masonry is not going to last that life without maintenance. And so here we're going to diagram it differently. We're going to have the same expected design life, the same masonry, so the arrows are connected. That is, it's one masonry veneer for the entire life, but it's reset every 15 years or so due to things like tuck pointing or other types of repairs. Okay, so what happens though when that intervention is not enough, as in this case, where we're having to reskin the building within 20 years, despite the owner diligently trying to maintain the building, it's ramping down over time. Each reset is not enough because the building is continuing to crumble, and we have to replace the veneer due to rampant defects in the construction. And the third concept is of a permanent component. In this case, the waterproofing behind the masonry. It is reasonable to expect that waterproofing is going to have to last for the life of the building because it's a concealed permanent component. It's not accessible for maintenance. And so this is a brand new brick masonry building. It's just opened. And if you look carefully, you see there's a lot of plywood in the windows. This is what it looks like from the inside after occupancy. So there's a total wipeout, right? So the sequence of events was that the contractor admits they're having problems during construction. They need more time to solve these construction problems that they're facing. But the owner demands that they finish on time because they're already booking rooms and meetings in the hotel. So the hotel opens on time. And then it rains, and the hotel closes. And then the owners unbooking rooms and meetings. Complete fail. Behind the masonry, we found huge gaps in the waterproofing, and worse, some structural problems. But the design line for this is one single straight arrow. That waterproofing needed to last, no intervention for the life of the building. And what we actually got was 6 months of performance before it had to be replaced. And as I said, there were structural problems. As Bobby will mention, one of the assumptions in anchored brick masonry veneer is that 2/3 of the width of the unit is supported on the gravity support system. That's not 2/3. In fact, that shelf angle didn't even reach the centroid of the brick, so it's really just kind of tipping it over. It's not really helping to support it. Right? So we then can get to the service life. So the service life is the actual duration of performance of the system selected. It's affected by many variables, including the system design or the demand that's placed on it, the product quality, or what we would call defects, the installation quality or construction defects, maintenance, or when it's deferred maintenance, we just call that neglect, and the climate and exposure. The same building in San Antonio is not going to last the same in Detroit. There is a difference based on exposure. So, with all of these building blocks, we can finally get to the concept of durability, and this is where the visualization really gets challenging, because it's an intangible proportional relationship that inherently is not visual. All right, so it is the service life relative to the design life that defines durability. If the service life equals the design life, then we would say that's normal duration, and we use terms like durable. So durable performance really means that you're meeting these expectations. So if I tell you that my razor lasted 3 months, you think, that's a pretty good razor. I want to buy that brand. That's great performance, right? Right? But if I tell you it was an electric razor, that doesn't sound so good anymore for 3 months of performance, right? What changed? Your expectation of how long those different razors should last. Less than 3 months on one hand, much longer than 3 months on the other. Durability is defined as that intangible proportional relationship between the expected life and the actual. And when those fail, that's when we get to premature failure. And with that, Bobby's going to give you a few examples of some brick masonry fails that we've investigated, and then come back to the code requirements. That is where we all come into play on this subject.
Mike's on. Okay. Podium mic works. All right, premature failure. So now we're going to talk about specifically the brick veneer. So we don't commonly get called to look at things that are performing well, installed well, or designed well. This is 10 stories up, downtown Austin. We're at the floor line. And what you can see is a 3/8 to 1/2 inch displacement of the upper brick veneer. What we'll be highlighting as we go through the code requirements is there's really 3 components in a masonry anchor that gets the load from the face of the brick back to your backing. The first is actually the anchor engaging the brick veneer. So unit to anchor. This one failed on that regard. This is what was actually behind it. And these are very thin corrugated brick ties that are now see-through in most places. So the next component in the load path is you need to get it from through the anchor into the backing. You can't do that if it corrodes all the way through. And then this one's a little harder to see. This is the attachment to the backing. This one is also in downtown Austin, different site. Wood frame construction, which is commonly going to have those corrugated ties. We actually have a 2-piece anchor, so we thought everything was going to be fine, except they were attached with a single roofing nail, only at the top. So these need to be, by the prescriptive requirements, at least an 8-penny nail, and at top and bottom, so you can actually adjust the tie. So this brick was rotating outward over the sidewalk. Now, I'm going to try to go through these as quick as I can. There's going to be a lot of information on the slides. I'm going to hit the high points because it's history, the code requirements. I don't need to read to you. So, going back to 1977, there was no consensus masonry standard. All the masonry requirements were within the model building codes. There was more than one building code, and each one had conflicting requirements. So depending on where you were actually designing, you had different requirements. In 1977, ACI and ASCE were strongly encouraged, despite them not wanting to form the Masonry Standards Joint Committee. This began the formation of the code and specification. It took 11 years, but the first MSJC code came out in 1988. One thing that's not on these slides is I'm born in 1989. So after that, TMS joins the MSJC. And what you get is the first code and specification of the three entities. And this was it. So this is the 92. If you look at depth, that's code and specification, not just the building code requirements, but also the construction requirements. And there's two separate documents bound together, so both the designer's requirements and the contractor's requirements are in one book. Similar to ACI 318, revisions to this document occurred every 2 to 4 years from 1992 to 2013. You get to 2013 and there's a little bit more heft. It's more than quadruple the length. Lots of research and testing. And still more to be done. So, we're still MSJC code. After 2013 though, the MSJC was dissolved. So it was 3 separate organizations working together. If anyone's been a part of any individual organization, it's hard enough to have one organization work together. Too many cooks in the kitchen. TMS was actually doing a bulk of the work on the 2013 cycle. So going forward, they just took over the code, and now it's just TMS 402, 602. It's if you reference ACI or ASE documents with the 2016 year, that document does not exist. So now we're going to actually use the codes. So we're going to start with the code requirements, which, as I said, there were 3 entities. This was called ACI 530, ASCE 5, TMS 402, all the exact same document. 2016 to present, now just called 402. Who's this for? Us, or the architect or facade consultant, whoever is actually putting together the design requirements for the brick veneer. And if you read the commentary, the code is not intended to be made part of the documents. Contractors should not be required to know the code requirements or implement them unless they're in a design build capacity. There are design decisions that come with the code requirements. You do not want your contractor making those design decisions. Then we have the specification. 530.1, ASCE 6, TMS 602. Why they couldn't all come together on their naming, I don't know. 2016 to present, just 602. Who's this for? This is for the contractors. So contrary to the code requirements, you can include a reference to TMS 602 in your specs and your general notes. That's what it's intended for. This is the general construction requirements that everyone has to apply to, and then you supplement that with all the design decisions that come from the code requirements. So, starting with the requirements, specification for wall ties has minimum embedment, minimum cover, and spacing requirements. That 2.67 might look a little odd to some people, but if you have a 16-inch stud, that's a 24-inch vertical spacing, gets you to that 2.67 square feet. That visually looks like this. So if you added no additional specification, this is what you could expect your mason to actually install. Notice all of our load path from the anchor to the brick, the durability of the brick, and the attachment of the backing is not in here because those require design decisions, which gets us into the code. Load path. It needs to be able to get through all 3 of those steps. So, IBC will reference sections 12.2 and 12.1 of 402. 12.1 is the general requirements, so this applies to both anchored and adhered veneer. I'm not talking about adhered today. That's when you kind of glue the stones onto the building. We're not talking about that. We're actually talking about that mechanical connection anchored veneer. So we have 2 design methods. One is alternative design. It's a single paragraph. It boils down to use engineering judgment. Then you have the prescriptive requirements, which is another 6 or 7 pages, and we'll go through, and if you meet specific qualifications, then it's a cookbook. Just plug in everything that's in the code. All right, to highlight what things need to actually be specified, I'm highlighting what's in 402 in red. Anything in white is already in 602. So, prescriptive requirements. We can't exceed a certain wind pressure if we use the prescriptive requirements. Our supporting elements have a pretty strict deflection limit. So if you're supporting on wood or steel and you're designing that for L over 360, if it's supporting the veneer, you need to up that, so it's L over 600. It needs to have 4-inch minimum bearing on the lintels, and it has a minimum unit size. So if you go back to those 602 requirements, there's 1.5 inches from the back of the unit and 5/8 from the front of the unit. That adds up to 2 1/8. By setting a masonry unit at 2 5/8 minimum thickness, you've got a 1/2 inch for the contractor to play with for construction. Now, starting from the outside in, anchor engagement.
Hey, I got a question.
Yeah.
If you go back to one slide, your veneer support deflection limit of L over 600 for your vertical, you're talking vertical load there, right?
Correct.
What is your limit for wind horizontal?
The horizontal limit, I'm not sure there is a specified limit in the prescriptive requirements.
The TMS don't have one. Yeah, that's what I was trying to verify. So one I could find was Griffin Institute of America had one that was for height over 600. Nothing for that in
No, that's not currently in 402. That must be, like you said, BIA also has a lot of tech notes available, so there are industry standards that supplement. Okay. So, anchor engagement. So, minimum bendment, that's in 602. Everything about actually the specification on a corrugated sheet metal anchor that would actually grip onto the mortar needs to be specified. Same with the wires, you got minimum size, you're trying to actually engage area of the mortar. And then the 2-inch minimum width on the wires. Next part, anchor durability. So this is the anchor in between the veneer and the backing actually has to last. We have cover requirements on the outside, minimum thicknesses of the material. Now, anyone who was fortunate enough to have Dr. Richard Klingner teach masonry, as I was, when he got to the specification section, the thing that stuck with me is he said, masonry structures have been around for thousands of years. Over time, the units and the mortar have only improved. Why on earth would anyone specify materials that have a 10-year expected life? I kind of stand with that. Galvanized is corrosion protection, but stainless is only 10% more. So next we're actually attaching to the backing, and it really depends on what type of backing you're using for these requirements. We're going to start with wood. Any anchor type is permitted. So corrugated sheet metal anchors, regular bent sheet metal anchors, adjustable ties, wire ties, all allowed with wood backing. It's attached directly to the studs with an 8-penny nail, not the sheathing, or something with equal or greater pull-out strength. You can install screws if they exceed the pull-out capacity of an 8-penny common nail. The thing that I've actually never seen done in practice is this requirement down here, and that is the fastener on a corrugated sheet metal anchor has to be located within a 1/2 inch of the 90-degree bend. If you look at the 3 anchors in the photo, that middle one meets that requirement. Perfectly bent 90-degree angle, fastener near the bend. Commonly, you're going to see the 2 on the ends. If you think back to those failure photos, that's kind of what they look like. If you think about how much that actually has to deflect before it engages the brick, you understand the need for this requirement. And like I said, I've never seen it done. It's a very strict requirement. There's so many requirements on corrugated sheet metal anchors. I would think twice before using them, but they are allowed with wood construction. Steel backing. Must use adjustable anchors. Cannot use corrugated sheet metal anchors with steel backing. You also need to, similar to the nail requirement, a number 10 screw. And you have to have a minimum thickness on your stud. Again, that's getting your load path actually transferred to the backing. Concrete and masonry, similar requirements. Can use anything but corrugated sheet metal anchors. So, recap, here is the 602 requirements that we started in the beginning. This is what the contractor has to put in. But everything we care about has to actually be specified. The properties of the anchor, the fasteners used to attach it. Everything is in there. And whether it's the architect, the structural engineer, or a facade consultant, all of these requirements need to get in the design somewhere. And if they don't, I won't complain, I'll just have more work. So. Future code requirements. So I'm actually on the 2022 code cycle 402-602, veneer and reinforcement connectors. The next code's actually a very long cycle, it's 6 years. They are revamping a lot of it. Veneer is the biggest one. What we anticipate changing in brick veneer is a completely rewritten chapter where there's currently those requirements kind of divided up across chapter 12. They're going to be condensed by anchor type and put into tables, so it's a lot clearer to actually find everything. You don't have to look in separate sections. The goal is, again, to make sure people actually use the code requirements. And then performance specifications. So that single paragraph for alternative design, there will be actually engineered design of veneer requirements going in there. So if you don't meet prescriptive requirements, you actually have a guide for what you can use. Each anchor type will currently have a capacity, a stiffness, everything required based on current research and testing. And ASTM is also working on new test methods. So the idea is the anchor manufacturers will begin to do their own testing, want to show that they exceed those performance requirements so they can sell more anchors. So we should get a lot more information over the next few years. And then I threw this one in kind of for fun for anyone who's ever sat on a code committee. As I said in the beginning, definitions are a very big deal. These will, going forward in 2022 and after, these masonry anchors that I've been referring to for 40 minutes or so will now be called masonry ties. The masonry anchors will be out. The idea is there were some people with very strong opinions. They thought there was confusion between anchors installed into masonry and masonry anchors. So your post-installed anchors will be anchors into masonry. Your accessory with your veneer will be a masonry tie. Very important to something. In summary, anchor brick veneer is part of the load path. All three of those phases need to be taken into account. We went over general durability concerns and in particular specific failure mechanisms of anchored veneer. We went over the history of standards, we went through the importance of the current standards, and we went over where the standards are headed. And I look around and most of you are still awake, so that will give us some time for some questions.